Go ahead and introduce Lee Orff now. He'll be talking about breakthrough simulation and visualization of an extremely violent tornado-producing thunderstorm.
Thank you, and that's what I'm going to talk about. So what are we trying to do? We're trying to understand what goes on inside of really big supercells that produce really bad tornadoes and what differentiates these from storms that do not. And in fact, it's very easy to simulate supercells that don't produce tornadoes. I've been doing that for quite a while. It's a little bit harder to get really weak ones, but it's very difficult to get extremely long, strong long track tornadoes. We have managed to do this, and what I've been focusing on recently is visualizing and analyzing this simulation that actually happened about a year ago. So about 90% of the fatalities occur in the biggest, strongest tornadoes. Long track just means the path is long. The potential for producing a lot of damage is much higher. So this is a little thing from YouTube. This is an actual thing that happened a month ago. Poor Sam Smith is driving down the highway and he sees a tornado and he doesn't run away from it, he just stops and watches and leaves us this great footage. So this is an EF4, this was near Rochelle, Illinois. This was only a few days after I actually came down to an NCSA and talked about tornadoes, so that was kind of creepy. But I'll pause it right about here, and you'll see there's definitely multiple vortex things going on. There's one of those vortices within this giant half-mile wide tornado. So you have vortices spinning around one another. This is the town of Fairdale, and here notice the cycloidal path of the multiple vortices in this tornado. So this is the kind of tornado we're trying to simulate, trying to understand better what's going on. So but we really don't know why some produce and some don't. We have some ideas, and a lot of field projects have helped us understand some of the factors involved. And in fact, observational work has indeed guided much of our choice of simulation parameters. And what blue waters is a critical ingredient for making this happen. We needed a supercomputer to do this. So what makes this work? You need the computer, you need the ability to handle a lot of data, and I'm almost ashamed to admit that over half of the time I've spent on this project is managing data, but it's actually very important if you're going to do very good visualizations and analysis. You do need a little bit of luck because the real atmosphere doesn't produce these storms, and neither do models, and that's good actually, because if the model was always producing these, that would be a problem. I'm using CM1 from George Bryan and NCAR. It's MPI and OpenMP, 2D decomposition, NetCDF I/O option. I did have to do a significant amount of work to modify the I/O regime. I'm using microphysics from Hugh Morrison, who's also at NCAR. That's also a critical ingredient in getting this to work. And I've spent a lot of time working with HDF. I started to use the core I/O driver, which buffers writes to memory. That seemed to be a really good way to go. I collect everything on each node and grow a file in memory, and then when the memory starts to run out, I flush it to disk, and it seems to run pretty well. We're only using 20,000 cores, about 2 billion grid points, a few days of compute time, 100 terabytes of data roughly made from the output of this model. So what we did was we took the environment adjacent to an actual storm that produced a long track EF5, and we triggered a cloud within that environment. So we grew the storm, and we used a different forcing mechanism that's been typically used in meteorology, which is called a warm bubble, which is, as it sounds, like a bubble of warm air. We actually use an updraft nudging technique to get the storm going. And of course, things never work out, and I won't tell you my sob stories about how I ran out of allocation right at the end. But anyway, we got the tornado to form, and I've been spending the last quite a while just analyzing the storm. So I'm going to share with you some of my visualizations and things like that. So all the stuff I'm going to show you was created from history files. I used Visit, and that's a supported Blue Waters application. I've learned a lot about it. I use it both in batch mode and interactive mode. I've been using Visit's compositing ray tracing algorithm to make many of the pictures you'll see. Also use Vapor from NCAR. It has its own data model. It's very good for doing trajectories, I've found. Both of these tools are absolutely indispensable for my work, and I'm very grateful for all the work that goes into making these tools. I'm trying to make, you'll see that some of the things that they can produce are quite nice. So the storm itself starts out as a classic supercell and becomes a high precipitation supercell. It's very dangerous. You see a lot of things going on between when the tornado forms an hour and a half in and then it's on the ground for 2 hours. This is a rendering of the rain and the cloud field during the strongest period of the storm. You'll notice that sometimes a tornado is sort of wrapped in rain, and these are very dangerous if you're trying to understand what's going on. You can't see the tornado. There's a lot of very small scale vorticity, what we call Myzel Cyclones in meteorology. These things kind of merge together to sort of consolidate vorticity. This is during the genesis phase. This thing right here is going to become the tornado. You can see there's a whole bunch of little tiny vortices that you wouldn't see unless there was maybe some dust to spin up, and they kind of come together. This thing here we're calling the Streamwise Vorticity current. I'll talk about that later. And this guy over here is actually an anticyclonic vortex. You see some very interesting vortex-vortex dynamics going on. You see some constructive interference and destructive interference. There's one particular anticyclonic disruptive event that happens. This is the tornado. This is an anticyclonic vortex that kind of consolidates. And then watch as it sweeps around the thing and gets sort of lifted up by the updraft. And after this event, this tornado is actually a bit weaker. And I'll show you more about that in a minute. And this thing we're calling a Streamwise Vorticity current is closely associated with those little vortices. It also seems to feed vorticity into the updraft of the storm. So this is actual just vorticity, and this is just the wind moving along the vorticity. So you have what's called streamwise vorticity, and there's a tornado, where the vorticity vector and the wind vector are parallel to one another. So this is a time series of the wind speed and pressure deficit, and this is actually a trace of the pressure deficit of the surface. So this is like the tornado track. So you see we get into EF5 territory pretty quickly. Once about, right about here it goes up. You've got winds of 130 meters per second near the ground. That's about 300 miles an hour consistently as this thing churns along. Here's the wind speed trace. So this is actually winds in excess of 130 miles an hour, meters per second, 300 miles an hour. Pressure deficits up to 150 millibars. Just an incredibly strong storm. So here's a movie of tornado genesis. This is rendered by Visit. This is the cloud field, and you'll see rain periodically coming in over here, especially in the rear flank of the storm. I'm going to slow it down during genesis. So here is the wall cloud, the tail cloud, and there's a descending condensation funnel. The tornado forms much in the way as we often see it in nature. That's good. We're going to look at the vorticity field in a little bit, and we're going to see that whereas the condensation funnel descends to the eye, the vorticity that actually seems to start at the ground and work its way up. So that's an interesting discovery. You see all sorts of unsteady behavior in the rear flank of the storm here. Notice how you see what looks like a strip of clouds that are kind of wrapping around into the wall cloud of the storm. That's actually relatively true, although the air is actually rising up through the cloud. So I'll show some of that in a little bit with trajectories. But it's a very realistic looking storm. This is really the first simulation of its kind. No one's ever done this before. So that's exciting. I've been sort of pawing through the data, wishing I had more time to look at it, but the summer's coming, so that's good. But anyway, this is 60 times faster than real time, just so you know. In order to see what's going on, it would go much slower. I'm dumping data every 2 seconds. Okay, so it's high temporal resolution. That's why there's so much, how much data I've been saving. So here's another way to look at it. This is the Mesocyclone. This is the updraft and the downdraft using volume rendering. This is with vapor. You can see the tornado forming right about here in the updraft field. This is the RFD, the rear flanking downdraft. This is a view from below, so you'll never ever see this view in the real world, but it's really cool. So you see this, what looks like a bookend vortex right here. There's a tornado forming. This is the Streamwise Vorticity current. I'll slow it down. And this is the rear flank downdraft. So everything's on its head, but it gives you a sort of a unique view into the formation of the storm and what's going on. It also makes you have to sort of rearrange your head and go, wait a minute, what am I looking at here? So now I'm going to put a sheet of particles near the ground and let them go. These are colored by the wind speed. So right over here, you see the strongest wind speed is actually in the cold pool associated with that streamwise vorticity current. Here's the tornado forming, and here's that current I'm going to be talking about. So the tornado's here. This is an anticyclonic vortex here. And the current of vorticity that's sort of feeding the updraft is this decoupled from the tornado itself, and you can see it forming right about there. So I'm trying all these different kinds of ways to interrogate the storm and visualize it in order to understand what's going on better. And so that's where these visualization tools come in really handy. So again, tornado genesis, I'm focusing on pretty low values of vorticity. So you're seeing a lot of vortices that are not very strong, but it does give you an idea that there's a lot of consolidation. You see vortex merging going on, and that does play a role. This white surface is the low pressure. So indeed, these are low pressure. You see cyclostrophic pressure deficit. Now I'm going to look at higher values of vorticity. I'm going to show you the storm over here as you saw before. And the blue is anticyclonic, the red is cyclonic, and this guy right here turns into the tornado. So there's actually some other vortices here that aren't showing up because of the threshold I've chosen. But watch this guy right here. It shows up from the ground upward. So this is probably about 500 meters deep or so. And you watch this guy go, and it sort of stretches upward. And now it starts to anchor itself. You start to see other little vortices right about here kind of merging in. So here's the tornado. One thing I didn't mention was, that tornado showed up on the ground before it did in the cloud field. So there's actual, and you see this all the time with chaser footage. You'll see debris spinning around before you actually see a condensation funnel. But many of these little vortex mergers are going on. There's a lot of vorticity coming together here. So that's interesting. But what I think is even more interesting is what you can't see in this movie, and that's this sort of lazy current of vorticity that's supporting the mesocyclone, which is the rotating updraft of the supercell. You see this tornado undergoing what's called vortex breakdown. This is something that has been seen in laboratory models, and you have two intertwined vortices. I'll go up the tornado to show you this. So you have two cyclonically rotating vortices that are sort of intertwined like a pretzel, and in between those two vortices is a strong downdraft. And that is called the two-celled model of tornado formation. So this is showing it quite faithfully. I think it's quite impressive, and I'm very excited about this. This is a result that we've never seen before in a full cloud model simulation. So on it goes, it churns away. I could show you this for a half an hour, run out of time. I skip ahead a little bit so I can get to that one anticyclonic disruptive event. I'll go a little bit slower this time so you can see what's going on. So watch this guy. Look at all the intricate vortex-vortex interaction that goes on here. So these are in 2-second intervals. You'll even see a little cyclonic vortex wrap around this anticyclonic vortex right here. So there it goes. And then it comes around, and that's wrapped up there. And then this guy gets wrapped around the tornado. And it's just very complex. It's like, I don't know how to explain it. That's why I like these animations. But what happens after this event is the tornado actually never really quite recovers. So it's as if it strips away some of the vorticity in the tornado. So this is that event. So here it's churning along at 130 meters per second, 150 millibar pressure drop, and it never really recovers from that. It's still a strong tornado. It's still EF3 or so, but it never quite comes back. So that's interesting. And there's times when the RFD over here is kicking out all this vorticity. It's very, very turbulent. And I'll go up the tornado here again, and if I didn't tell you there's a tornado there, you might not even know it because you have, all these, it's just a mess. And inside of this bundle of mess is still a relatively coherent vortex. And you'll see as I let the movie go again, that you can sort of pick it out again. So there it is, there's our tornado. It's like an EF3 or so. You still see lots of more interesting vortex stuff going on. Again, it goes on for quite a while. So now I'm going to focus on this feature called a Streamwise Vorticity current. So that's this guy that's kind of entering the general circulation of the updraft of the storm. So there's a tornado. There it goes, churning along. And we're looking towards the east. So this is along the boundary of the forward flank of the storm. And you see all this vorticity that is just kind of ingested into the storm. It's being tilted upward and to vertical vorticity, which is what supercells are all about, rotation about a vertical plane. And within this vorticity bundle, or whatever you want to call it, you can see the whole thing is rotating. It's just a really dramatic illustration of how all this consolidated horizontal vorticity is sort of being tilted into the updraft of the storm. And that must be helping drive the strength of the storm. So here's a bunch of particles. Notice that indeed it's streamwise. I mean, the vorticity and the velocity vector are along the same thing. They're moving in the same way. This is probably one of my favorite renderings of this SVC. It's just, it just shows what's going on. And you can tell that it's not affiliated directly with the tornado. It's feeding the outer reaches of the tornado vortex or the mesocyclone. It's hard to really say where the mesocyclone, which is the rotating updraft, ends and the tornado begins. In these high-resolution simulations, it becomes a little more, it's turbulence. It's much more turbulent. And some of the standard models that we have, extremely useful, and we certainly haven't disproved any of them, are a little less, it's a little more complex than that. So now I'm just going to do parcels. I'm coloring them with vorticity magnitude, so you can see these little bursts of vorticity along that region there. You can see how it's transferred upwards. This is the core of a tornado, so this is actually a downdraft. You can see the vorticity is strongest there. So there's all these different techniques we can try to sort of, figure out what's going on. It's rotating, no doubt about it. And again, the strongest vorticity right now is right in the center in the core of a tornado, which is consistent with theory as well. So I played with different thresholds. It's really fascinating. Vorticity makes a really good tracer often in these simulations. It's validated by throwing parcels in. The parcel paths, by the way, are being integrated by the Vapor software, whereas the vorticity field's been saved to disk, and they agree so perfectly. It's just really good. Vapor's doing a very good job of integrating parcels from the history field data. So now I'm going to try putting parcels in different locations, trying to sort of develop a conceptual model. This is the Streamwise Vorticity current. This is air in the cold pool that seems to be feeding the tornado. The rear flank downdraft is this light blue that is also getting in. But when you have an updraft that's this strong, pretty much everything's going to go up at some point, right? It doesn't matter where you drop the parcels, everything's going to go up. But it's sort of like the layers of an onion when you start looking at where the air that feeds the tornado originates from. And that's an important question in meteorology. Interestingly enough, it doesn't seem like a lot of the air that feeds the tornado comes from the warm side, which is interesting because it's easier to lift warm air than it is to lift cold air. But the air in the cold pool in the simulation is not super cold. And that's a tribute to the microphysics, the Morrison microphysics. We have cold pools that are much more realistic. So now we're going to go towards the end of this tornado's life. This is using vapor, just looking at the cloud field and the buoyancy field. So this is the boundary of the cold pool. You can see some of those little vortices in the cold air, evidence of them. You can see vortices that are horizontal, that are rising up the tornado cyclone itself. Lots of really intricate vortex-vortex interaction going on. You'll see the tornado weakening, and the condensation funnel will begin to lift, as you see in nature as well. Again, this is running 60 times faster than real time, so a real tornado would be dancing around that fast. So here's an interesting multiple vortex event that occurs. Again, these are in 2-second slices. When you have a fast rotating vortex that's actually moving quickly, you have the translation and the rotation added together at one location. You get these really strong swaths of wind, and I believe those are responsible for a lot of the damage that occurs. So now we're going to watch the tornado decay, and don't blink because you might miss it. We're looking at wind vectors at the surface, and it's gone. It sort of decays in a grandiose downdraft. I did my PhD thesis on microbursts, so I was kind of happy about that. So you see a little microburst form right there, boom. So you see this rotational flow turn into divergent flow, all in the course of like 20 seconds. And this is interesting because oftentimes tornadoes will do what we call roping out. You'll see them sort of stretch out like the Wizard of Oz tornado where it kind of stretches out horizontally. This one just holds on for dear life until the end, and then it pretty much decays along its length almost instantaneously, like over the course of 30 seconds, much like when it formed. So here's another view of decay. This is rain and pressure deficit, so these are vortices. There's a tornado, and it looks like it gets pummeled to death by rain. At least that's what the visualization suggests, but there's many things that can cause downdrafts. Clearly there's sinking motion going on here, but it could be due to negative buoyancy from the air. It could be frictional drag from the hydrometers. It could be could be pressure terms, so it could be pressure that's drawing this down. This hasn't been unpacked yet. We've got a lot to do, but what's really exciting about the simulation is we've caught the genesis of a tornado, the maintenance phase, which is very long, and then the decay phase, and each of these phases are things that meteorologists are very interested in understanding more about. So my parting thoughts, well, this is possible. You can do this. It's been done. Blue water's played a large role in this. We see consolidation of vortices, this feature we're calling as streamwise vorticity currents, important in tornado genesis and maintenance. You see a lowering of the pressure beneath the updraft as the tornado forms. You see the vortex forming near the ground and sort of stretching upwards. It's nearly instantaneous. The tornado maintenance phase is very long. You see a lot of morphologies going on. It's quasi-steady, but there's a lot of unsteady behavior there. And then, decay is associated with lots of downdrafts. So future work, I'm hoping to be involved in the Cadence project. We hope to do parameter studies or ensembles at this resolution. I want to do higher resolution. I want to apply to more storms. I want to properly include surface drag. I might change my I/O regime. Please talk me out of that because my current I/O regime works, but I want to make it better. And I want to work with the visit programmers to deal with a really nasty issue that I have, at least, with trying to get really high fidelity volume rendering when using lots of cores and lots of samples per ray. And that's my talk. Thank you.
You didn't say which equation is this one, large AP simulation?
Yes.
So, how many cells? How many?
1.8 billion cells, 30-meter resolution.
How about the boundary condition?
Outflow boundary conditions, free slip at the surface. Free slip at the surface, which is, it worked. That's all I can say.
Then you're adding the energy equation. You're solving the energy for temperature.
Well, we have potential temperature is the prognostic variable. So you've got buoyancy, you've got advection, you've got, you know, all those different terms.
It's a conservation equation.
Yes.
And then you had the droplets, I mean rain, you mentioned rain.
Yes, so we have microphysics, so we have mixing ratios for rain, cloud, ice, snow, grauple, and water vapor, and I forgot one. So we have prognostic equations for all those, and also the number concentration for some of those. It's a dual moment scheme.
So I'm also interested in boundary conditions. So did you have a hot and cold dividing line in the simulation?
No, so this is horizontally homogeneous. It starts out as a horizontally homogeneous base state, and then you perturb that base state. That's it. The surface boundary is free slip, and the outflow. We have outflow boundary conditions, and the box moves with the storm. So you can keep the tornado centered.
Oh, I see.
That takes some trial and error, of course.
Oh, that's interesting.
Yeah. We translate the domain with the storm.
Because it looks like there was flow coming in from the boundaries, and so
Sure. That's allowable. I mean, it's
what's the physics? Because
just outflow, horizontal outflow boundary conditions. I can point you to some
pressure
paper.
in the center is just drawing stuff in, and that's causing the vorticity when it comes in.
Well, no, I mean, the updraft is pretty much doing everything. I mean, it's causing all of the, and there's mass flowing out of the domain in the laterally, and there's mass coming in. You can run into issues with domain-wide pressure changes when you have too much mass exiting and not enough mass coming in, but we don't have that problem with the simulation. We made the domain big enough. So I'm only showing you a small portion of the domain. It's actually much bigger than what you're seeing, so that handles a lot of these issues. We keep the storm in the center, and we don't have a lot of issue with boundary issues.
And what's your vertical resolution, and how high is it?
30 meters, 20 kilometers. We do stretch above 10 kilometers. We do have a stretch. We do have a horizontal stretch and a vertical stretch, but the main action is isotropic 30-meter grid spacing, and that was important.
In all dimensions?
In all dimensions. So it's 10 kilometers up, 60 kilometers on a side, and then the whole domain is 120 kilometers. So we have the horizontal stretch goes out to 120 kilometers.
Okay, I think we've got time for one more.
Have you looked at the source terms for the vorticity on that current, whether it's from the temperature gradient or shear along that boundary?
Not yet. There's a lot of analysis to do. It's most certainly related to buoyancy gradients. So we have cold air adjacent to warm air that produces horizontal. It's pretty simple in that case, but you're right. There's a lot. I need to do that, and I need to do a lot. In fact, the analysis portion has just begun with this storm. One more question?
Do you know what the effect of the subduction is?
Yeah, so we've got Smagorinsky turbulence closure. Again, it worked. We were using a TKE type closure. We had to do a lot of simulations to get this before this one worked, and in fact, this is what worked. That's all I can say. So it's a Smagorinsky deformation-based turbulence closure.
Okay, we'll have to take the rest of the questions offline, I think. We'll get our next speaker up here.